So my name is Emmanuel. I'm the Ames Canada Junior Research Chair in Data Science for Climate Resilience. I'm a lecturer at Stellenbosch University in the School for Data Science and Computational Thinking, and I'm also with the Department of Industrial Engineering. And I lead the Data Science for Ecosystems Research Group at Stellenbosch University. Before I go on, I just want to thank various institutes that have helped. The IDRC, the Government of Canada, AIM South Africa, the National Institute for Theoretical and Computational Sciences, and Stellenbosch University. So I'll be talking about compressed sensing within the context of bioacoustics. But before I do that, I want to just introduce you to a new research group that you might not have heard of yet. We're still fairly new. So we're called the Data Science for Ecosystems Research Group at Stellenbosch University in collaboration with the African Institute for Mathematical Sciences. And our goal is to be a leading research group in addressing conservation problems using machine learning. And we started, I guess a few months ago. We started earlier this year. There were only 2 members, myself and Professor Kanchikan Rajaratnam, who's the director of the School for Data Science, and now we have 18 active members from various places, and there's a map that kind of shows our impact so far that we've managed to achieve. And we have a very diverse group, and I think that's what will help us succeed as a group. We have computer scientists, mathematicians, ecologists, and we also have a world-renowned quantum physicist. So please reach out to us if you would like to collaborate. Okay, so now about compressed sensing. So basically the idea with compressed sensing is that it allows us to compress data and effectively reconstruct the data in such a way that the reconstructed data is as close as possible to the original audio data. And the idea with the compression is it's extremely fast. We want it to happen in 1 or 2 seconds. And so when I say compression, I want you to think about just like compressing your audio files using like a zip. But it has to happen in like 1 second. So why is this interesting for us in the bioacoustics community? Well, there's two possible ways to think about it. We can now start to think, well, can we do compression at the source on our automatic recording units? So these little devices have the micro SD cards, and the micro SD cards have limited memory in them. If you're using, for example, 128 gigs, and your memory card might run out faster than your battery runs out. So it would be great if we could store more data on the memory cards. And this is an African Bioacoustics Community Conference, so we have to take into consideration the African budgets in certain projects, where not every research group can afford large micro SD cards. So these micro SD cards aren't exactly cheap. Like a 256 gig Extreme Pro card is more than 500 rand. And if you have 50 of these units, the budget starts to become a bit of a problem. So we need to think about the African context. And also, if we could compress data at the source, then we don't have to go to the recording units as often to swap out memory cards. The other way to think why compression is interesting is, what if we could think about data transmission? So instead of having to go to the field so frequently, what if we could transmit the data from our recording devices back to some server to effectively process our data? And this would allow us to start to think about real-time machine learning to deploy our classification models on these little recording units and to send back information to a server where you can check, how's my model doing? Is it classifying species correctly, or is it making mistakes? So to help with this, I made up a little hypothetical situation where we're somewhere near the camp, and let's pretend that all your favorite recorders are deployed somewhere in the field. And let's pretend that the distance between the recorder and where we are is a fairly long walk and maybe complicated to gain access to. So wouldn't it be great if we could start to think about having machine learning algorithms directly on these units and a means of transmitting the data back to our local servers so that we can verify the models and verify the data. And we also have to factor in the fact that the internet connection might not be strong, right? We might not have a 4G or a 5G network. We might have a really weak network, so we want to compress the data and compress the models such that we can do this. So the research question effectively is, can we compress data at the source on our recording units by a significant amount, so like 70% compression? Can we do this compression extremely quickly in about 1 second? can we make it computationally very inexpensive so it doesn't drain the battery life on these units? Then can we reconstruct the audio signals back to the original format and apply machine learning algorithms such that the machine learning algorithms on the reconstructed data is nearly as effective as on the original data? Okay, so I carefully titled the slide, Compressed Sensing Without Being a PhD in Mathematics. Even though I had a PhD in mathematics, some of the stuff is still complicated. So there's two main components. There's the compression phase and the reconstruction phase. The compression phase kind of works like this. So let's say we have a sampling rate of, say, 16,000 hertz. That means in 1 second we have 16,000 data points. So the compression, so we pick a compression rate, say 50% compression, and then what we do is we just randomly select. So you would store your data as a vector of amplitude values, and you would just randomly select those 8,000 points. So that's how the compression works. Then the reconstruction is a fairly complicated mathematical operation. Basically, in a nutshell, it involves using optimization algorithms to solve undetermined systems of equations. Basically, that means that we have more variables than equations, and we're using some kind of L1 optimization to do the inverse operations to reconstruct the data. Now, this goes against what we know, right? Based on the Nyquist theorem, we're now reducing the sampling rate way below what the Nyquist theorem states. So the data used to start to get some empirical results was the Cholo-Alethi data, which was presented on Monday by Moses. So we had about 29 hours of data of the vulnerable Cholo-Alethi, which was collected in Malawi. It was collected by Ruben from Binko, Tiwange from WESM and Malawi University of Science and Technology, and Moses, who's somewhere in the room here. So there's a picture of the Cholo-Alethi, and I'm just going to play some of the audio. Let me just reduce the volume of those. Okay, so as we know, one of the best parts about being in this job is you get to listen to nice sounds all day long. So what we did is we built a public data set. We used machine learning algorithms to help us to find these calls, and we manually verified the data. And we released the data on Zenodo, so the audio files and the annotations, and you can import this using Sonic Visualizer, which is an open source software. And basically the reason for doing this is because in other areas of machine learning, people encourage benchmarks. So you have a method, you have data, and you want people to effectively improve the results. So all our data is publicly available for other machine learning people to try and improve the models continuously. So we use convolutional neural networks to address this, and Logan spoke about this a little bit the other day. But the particular approach we use is called transfer learning. And the idea is kind of like this, where you build some model on some problem X, where problem X has a very large data set. And then you reuse the model along with its parameters to solve some problem Y, where problem Y actually doesn't have a lot of data set. And this makes a lot of sense in the case of ecological studies for critically endangered animals, because you would have a lot of background noise, but you wouldn't have a lot of data of the vocalizations. And the full methodology is detailed in this paper. But the methodology for the compressed sensing kind of works like this, where we have the original data that was maybe sampled at 6,400 hertz. Then from there, going to the right, is you would create your original spectrograms, and then you would apply the convolutional neural networks to classify the data. Then from there, we take the original data, and then we randomly select 23%, so effectively a 77% compression rate. Now we have our compressed data. Then we do the optimization technique to reconstruct the data. Using the reconstructed data, we can now create the reconstructed spectrograms and then train the same convolutional neural network, so the same model on the reconstructed spectrograms, so that it's a fair comparison. And then we can compare if we use machine learning on the original data and machine learning on the compressed data, and how does that work. So let's say we have some original acoustic data that has, let's say, 410 gigabytes. If you were to use just a conventional zipping compression scheme, you would bring that down to around 394 gigs, so effectively 4% compression. If you were to use a tar or 7-zip, you would bring that down to 386 gigs, so effectively 6% compression. And if you were to use compressed sensing and some other modifications, you could bring that down to 103 gigs and have 75% compression, and you can do this in about 2 seconds. If we now compare the machine learning algorithm on the original data as opposed to the reconstructed data, we only have a loss of 1% in classification accuracy. So on the left, here's a vocalization of the Cholo Anithi call. You can see a little bounding box. That was sampled at 6,400 hertz. And on the right is the reconstructed spectrogram after undergoing 70% compression. And you can still see the Cholo Anithi call. So that's kind of what the spectrogram looks like after the decompression. So what does this mean for all of us? Basically, it means that we should now start to think about model compression. These neural networks have millions of parameters that are being optimized, and deploying these on small devices like Raspberry Pis that's shown at the bottom there, it uses a lot of battery power. So we can now start to think about making these models smaller and smaller, such that we can start to do real-time conservation. And we can also start to think about data compression, so that we can send data back to a remote server, so that we don't have to be going back and forth to the field in potentially dangerous environments, and maybe the battery hasn't run out, so we can actually store more data. So we can start to think about real-time conservation. So that allows for avoiding frequent expeditions into the field. So these are fairly early empirical results, but I think it has potential to do something useful. And there are I have a few master's students. I have a new mathematician who's going to be working on this as well, because we want to make some of these things faster. And I guess the main takeaway message, if you weren't paying attention, is that in my opinion, there's a real need to start to work on real-time conservation. And I think that computer scientists and machine learning people, mathematicians, and other fields as well, physicists and statisticians, can play a big role. So I guess the takeaway message is to start to think about collaborations with people in different disciplines to start to work towards real-time detection. So thank you very much. Please feel free to reach out, and yeah, thanks.